Hello and welcome back to Educator.com and welcome back to physical chemistry. So today we're going to start on the next major broad topic of physical chemistry, which is molecular spectroscopy. So we've done the thermodynamics, we've done the quantum mechanics, and now we're going to bring that quantum mechanics to bear and talk about probably what's the most important topic as far as practicality is concerned for the chemist, because pretty much everything you do as a chemist is going to be some spectroscopic technique. So we'll be discussing the theory behind molecular spectroscopy. Let's get started. Okay, so molecular spectroscopy studies the interaction between matter and electromagnetic radiation. So molecular spectroscopy. Hope I spelled that right. Okay, studies the interaction of molecules with electromagnetic radiation. That's it. That's all it is. We hit molecules with certain amounts of radiation in different regions of the electromagnetic spectrum, and we see what happens. That information gives us most of the information that we have about what's happening inside the molecules and how molecules behave. So we will be concerned with three regions. Of the EM spectrum. Okay, we're going to be concerned with the microwave region. So microwave region is related to rotations. So when there you go. So when a molecule is hit with microwave radiation, there are changes in the rotational state of the molecule, the rotational quantum state of the molecule. And then we're also going to be concerned with the infrared. The infrared vibration. So when a molecule is hit with some infrared radiation, changes in the vibrational levels of the molecules take place. And most of you have already done a fair amount of IR spectroscopy from your course in organic chemistry. So, and then of course, the last is visible and ultraviolet. So in the visible and ultraviolet range, electronic transitions. That's when it's in this range, the energy of the visible and ultraviolet range, where electrons actually move to higher states themselves, electronic states. Rotation, vibration, electronics. So there's rotational spectroscopy, vibrational spectroscopy, and electronic spectroscopy. Okay, so let's see. So the absorption of let me see, how do I want to do this? Okay, so the absorption of microwave radiation, as we just said, we have rotational transitions. Now, in the IR, not only do we have vibrational transitions, but accompanying those vibrational transitions, there are also rotational transitions. So I'm going to say vibrational plus rotational transitions. And as you would expect, in the visible UV range, we have not only electronic transitions, but there's so much energy there that that energy causes an electronic transition, it causes vibrational transitions and rotational transitions. Plus vibrational plus rotational transitions. So all transitions take place when you're hitting it with energy in the visible and UV range. Most of the information that we get from spectroscopy, we actually get from electronic spectroscopy. Electronic spectroscopy allows us to, it's difficult to analyze, but everything that we need is there. It gives us information on electronic states, on vibrational states, on rotational states. The rotational spectra, the vibrational spectra, tend to be easier, but they don't give us as much information. So the electronic spectra gives us all the information that we want. Okay, so let's see. Now, the frequency of the absorbed radiation The frequency of the absorbed radiation is, well, it comes from this, we already know this, delta E equals h nu. Planck's constant times the frequency is the change in energy from one energy state to another. So if we solve for the frequency, what you end up with is the frequency of absorption is going to equal the change in the energy between the two states divided by Planck's constant. Or we can say the energy of the upper state minus the energy of the lower state divided by Planck's constant. That gives us the actual frequency that we observe in the spectra. That's what we're going to see on the spectrum. So when we see a line in the spectrum or a peak, it's this number right here. That's what that is, and it comes from this relation. So now what we're going to do, we're going to use the energies for the rigid rotator, the harmonic oscillator, and electronic energies to find this difference, because we want to find an equation for what is the absorption number. Now, in spectroscopy, in general, frequencies, I'll put it in parentheses, frequencies are listed in something called wave numbers. We've seen them before. Frequencies are given in wave numbers. So that's what we're going to be working in, are given in wave numbers, which is just the inverse of the wavelength. So inverse centimeters, wave numbers. And in general, it's going to be inverse centimeters. Now, the wave number, anything that's in a wave number is going to have a tilde over it. Well, that's equal to 1 over lambda, or my preference, it is equal to the actual frequency that we got from the other equation, just divided by the speed of light. That's it. So if you get a frequency, if you divide that frequency by the speed of light, you're going to end up getting your wave number. That's all. Now, we said transitions. Between vibrational states. Those states are accompanied by transitions in rotational states. Are accompanied by transitions between rotational states as well. Rotational states as well. Okay, the following discussion is going to apply to diatomic molecules. So we'll discuss polyatomic molecules, but for right now we're just going to talk about diatomic molecules, homonuclear and heteronuclear. So the following discussion, and for several more lessons, the following discussion applies to diatomic molecules. Okay, so let's begin with the energy of the harmonic oscillator. The energy of the harmonic oscillator, HO, is energy that's based on the quantum number R, it's the vibrational quantum number, is equal to h nu times r plus 1/2, where r takes on the values 0, 1, 2, and so on. When r is equal to 0, we have 1/2 h nu. That's the energy of the ground state. So quantum number, when the quantum number is 0, put it into the equation for the energy, and what you get is the ground state energy. So we see that there's always some vibrational energy. It's never 0. Okay, now where nu, this frequency, is equal to 2 pi times the force constant of the molecule divided by the reduced mass to the 1/2 power. Okay, and this nu is called the fundamental vibration frequency. Is called the fundamental vibration frequency. you'll sometimes see it as nu sub 0, something like that. Now, K is the force constant. K is the force constant of the bond. How springy the bond is. Is it really, really tight, or is it really, really loose? And mu is the reduced mass. So we've seen the reduced mass before. That's it. So I just want to make sure that we understand what all of the parameters are. Okay. There are selection rules for vibrational transition. So the selection rules for vibrational transitions. And those selections rules are that delta R equals plus or minus 1. In other words, if it's going to make a transition from one vibrational state to another, it's going to go from 1 to 2, 2 to 3, 3 to 4, or 4 to 3, 3 to 2, 2 to 1 in the case of emission, absorption up, emission down. As far as the harmonic oscillator is concerned, it's only going to go one or two steps. I'm sorry, one step up or one step down. It's not going to go from 1 to 5, from 1 to 4. If it's going to make a transition from 1 to 5, it's going to pass through 2, 3, 4, and then to 5. That's what that means. Those are the transitions that are allowed. The other transition rule is the dipole moment of the molecule. The dipole moment of the molecule must vary during a vibration. Okay, must vary during a vibration. I wouldn't worry too much about this whole, this idea of the selection rule and how a dipole moment is related to the selection rule. This is often called a gross selection rule. The name itself doesn't really matter. So the dipole moment of the molecule must vary during a vibrational transition. All this means, so this doesn't mean that the molecule has to have a permanent dipole. It can or it cannot have a permanent dipole. In the case of a molecule like hydrogen chloride, it has a permanent dipole. In the case of a molecule like N2, well, they're both the same. It's homonuclear, so there is no permanent dipole. Now, these are actually not the best examples to use, but what we mean by the dipole, it has to change during the vibration. So it doesn't have to have a permanent one, but if the molecule, if somewhere during the vibration a dipole shows up, then it's capable of a vibrational transition. Again, the one that we're going to be concerned with most of all is the changes in the quantum numbers itself. In this case, delta R equals plus or minus 1. But it's good to know this because some of your classes, depending on what they're going to cover or what they're not going to cover, they may actually go into the mathematics behind this. I don't know. We ourselves are not. We're going to be concerned more with just the spectroscopic aspects. Okay. Now, as we said earlier, excuse me, said earlier, spectroscopy is conducted primarily in wave numbers. As we said earlier, spectroscopy is conducted in inverse centimeters, in wave numbers. So we want to take this thing, this equations for energy, and convert them to wave numbers. Okay. For vibration, the symbol that we use is G. So G as a function of R is equal to the energy of R that we had from the previous page divided by Hc. The energy that you have, the energy that's given in joules divided by Planck's constant divided by the speed of light, any energy in joules divided by Hc is going to give you the number in inverse centimeters. So this is called the vibrational term. And this is what you'll see in the literature. This G of R, called the vibrational term. And it's just a symbol for the vibrational energy expressed in terms of wave numbers, expressed in inverse centimeters, as opposed to joules or anything else. So G sub R, not G sub R, sorry, G as a function of R is equal to, well, the E of R is H nu R plus 1/2, and we're going to go ahead and divide it by Hc. The H's cancel. Okay, what we end up with is this nu tilde. Okay, so it's the frequency expressed in wave numbers, r plus 1/2. Everything else is the same. R is going to take on the values of 0, 1, 2, 3, and so on. And the reason it's here, we're left with n over c. Well, remember what we said? That is just equal to n over c. That's it. So, g of r is equal to nu tilde, frequency, the fundamental vibration frequency expressed in wave numbers, times r plus 1/2, where nu tilde is equal to this nu over c, which is equal to 1 over 2 pi c k m. That's it. It's just a little bit of mathematical manipulation. That's all. So this is the important thing right here. This is what we have. This gives us the energy of a particular vibrational state depending on the quantum number r. So let me go ahead and put r equals 0, 1, 2, and so on. It gives us the energy of that particular vibrational state expressed in inverse centimeters. That's all this is. Okay. Now, so that's the energy of the harmonic oscillator. Now let's go ahead and talk about the energy of the rigid rotator. So, the energy of the rigid rotator. Oh, in case you're wondering why it is that we're talking about the harmonic oscillator and the rigid rotator again, these things are models for spectroscopic movement, spectroscopic transitions. The harmonic oscillator is this way. It's a molecule that's vibrating. So the mathematics behind this is what we're doing. The rigid rotator is something that rotates like this. So when you have a diatomic molecule that's rotating, we model it with the mathematics of the rigid rotator. That's all. That's what we're doing here. So the energy of the rigid rotator is, well, in terms of what it is that we studied earlier, Ej equals h bar squared over 2I times j plus 1, where j is the rotational quantum number, and that takes on the values 0, 1, 2, and so on. Here, I is the rotational inertia of the molecule. It's equal to the reduced mass times the equilibrium bond length, the radius, the length between the two nuclei. This E stands for just equilibrium squared. That's it. So this is the moment of inertia. This I is the moment of inertia, or the rotational inertia, is the moment of inertia, or the rotational inertia of the molecule. And Re is the equilibrium bond length. Equilibrium bond length. One of the parameters that you'll see when you look at a table of constants of spectroscopic data is you're going to see the R sub E. You're going to see the equilibrium bond length for that molecule. Now, the rotational state, this gives the energy of the rotational state, the degeneracy of each level. In other words, the number of levels that actually have this energy, the degeneracy, is equal to 2j plus 1. Okay. Now, when we discuss the rigid rotator, degeneracy is not going to play too well. That's okay. When we discussed the rigid rotator earlier, I don't think I explained why this degeneracy exists. I may have, but I don't believe that I did. I think I just sort of threw it out there as a number. I don't think I explained where this degeneracy in the rotational states comes from. Explained the nature of this degeneracy. Okay, here's what's going on. I'll tell you, and then I'll write it all out. So J is, let's say, 1. That's going to have a certain energy, so it's going to rotate with a certain energy. However, for each quantum number, in this case 1, there are 2 times 1 plus 1, so there are going to be 3 actual orientations in space, fundamental orientations, where the rotation is going to have that energy. So that's what degeneracy means. It's going to be a particular quantum state that has that same energy. That's what the degeneracy is. I mean, we know that by definition. Well, the orientation in space of a molecule doesn't affect its rotational energy. In other words, if I have a certain molecule that's oriented this way and it's rotating like this, or if it's this way rotating like this, or if it's this way rotating like this, they have the same energy. So that's what this degeneracy means. In the case of j equals 1, you have, it can be this way, it can be this way, it can be this way. If j equals 2, that's 2 times 2 plus 1, that means there are going to be 5 fundamental orientations in space that give you that same energy. It's going to be 1, 2, 3, 4, 5. That's what's happening. For 3, you're going to end up with 7 levels of degeneracy, 7 fundamental orientations in space that all have the same energy. That's the nature of this degeneracy of the rotational states. Now, let's write it all out. So, and give you a little bit of the quantitative aspect of it. Very little. Okay, a molecule's orientation in space. Orientation in space has no effect on its rotational energy. Has no effect on its rotational energy. J is the quantum number that represents the angular momentum of the rigid rotator. In other words, we know that anything that rotates has an angular momentum. That angular momentum is going to be perpendicular to the direction of rotation. So if a molecule is rotating like this, its angular momentum is that way. The magnitude of that angular momentum, that's what J is. J squared, actually. Well, that's what it represents. It represents the magnitude of the angular momentum. If it's rotating this way, the angular momentum vector is pointing that way. If it's rotating this way, it's pointing that way. Now, this is the z-axis, okay? So it could be rotating like this, like this, like this. So angular momentum pointing that way, angular momentum vector pointing this way, angular momentum vector pointing this way. Now, for each value of j, there is a j sub z. It's the component of the angular momentum vector along the z-axis. J sub z is, we've already seen this before for angular momentum, for rotational angular momentum. We've seen this for spin angular momentum already. Jz is the component of the angular momentum vector along the z-axis. The z-axis. Jz, it takes on the values 0, plus or minus 1, plus or minus 2, all the way to plus or minus j. So if j is 1, then what we have is 1, 0, minus 1. If j is 2, we have 2, 1, 0, minus 1, 2. If j is 3, we have 3, 2, 1, 0, minus 1, minus 2, minus 3. It's a projection of the angular momentum vector along the z-axis. All of those orientations in space carry the same energy given by the... So here is where your 2j plus 1 comes from. There are 2j plus 1 values of j sub z. So for each j, there are 2j plus 1, I'll just call them fundamental orientations. The fundamental orientations with the same energy. Okay. Now, when we discuss the hydrogen atom, when we discussed the hydrogen atom, we called J, we called it L, the angular momentum quantum number, the rotational quantum number. And we called this J sub Z, we ended up calling it M sub L. That's it. This was a magnetic quantum number. That's all that's going on here. Remember, for each value of L, you have 0, plus or minus 1, plus or minus 2, all the way to plus or minus L. That's it. It's the magnetic quantum number, which takes on the values. Number 0, plus or minus 1, plus or minus 2, all the way to plus or minus L. That's it. Okay, so now we'll do the rotational term. So we went ahead and expressed the vibrational energy in terms of wave numbers. Now we're going to express the rotational energy in terms of wave numbers. The rotational term is symbolized as f of j. Now, f of j is equal to E of j divided by hc. It's equal to h bar squared over 2I hc times j plus 1. Well, h bar is equal to h over 2 pi, so that implies that h bar squared is equal to h squared over 4 pi squared. So when we put all of this back into here, we get that the rotational term, in other words, the rotational energy expressed in terms of wave numbers, is going to be equal to, well, that's fine. Let me write it all out, actually. H squared over 8I pi squared hc times j plus 1. We get some cancellation with the h and one of these. So we're left with, what we're left with is f of j is equal to h over 8I pi squared c times j plus 1. And again, j takes on the values 0, 1, 2, 3, 4. This thing right here, actually I'll circle the whole thing, not just the bottom part. This whole thing, this is called the rotational constant. Rotational constant. And is symbolized as a B with a tilde on it. This is another one of the spectroscopic parameters that you find in a table of data, a table of spectroscopic data. It's, just like you see the equilibrium bond length, you'll also see the rotational constant. And as we go on with the lessons, you'll see that there are more and more constants that are actually tabulated. So, since that is symbolized that way, we'll go ahead and write it as, so f of j is equal to b tilde times j plus 1, where j takes on the values of 0, 1, 2, and so on. And b is, of course, what we just said. F of j is now in inverse centimeters. Now the selection rules. Okay, so the selection rules for rotational transitions. For rotational transitions, delta J equals plus or minus 1. That means it can only go from one rotational state to the next, either up or down. It's not going to jump 5 levels. And in this case, the molecule must have a permanent dipole. So in the case of a rotational transition, it has to have a permanent dipole. In the case of a vibrational transition, there has to be a change in the dipole moment during the vibration, during the transition, if the transition is to happen. It must have a permanent dipole. That's the difference between the two. Okay, now we have the rigid rotator energy, we have the harmonic oscillator energy. Therefore, like we said, the transitions in the infrared, the vibrational transitions, are accompanied by rotational transitions. So the combined energy of the transition is going to be the energy of the rotation plus the energy of the vibration. So the harmonic oscillator rigid rotator approximation for the energy of the molecule is therefore the sum of the vibrational and rotational energy. The sum of the vibrational and rotational energies. Therefore, the energy Rj is equal to, well, it's equal to the vibrational term plus the rotational term, the vibrational energy plus the rotational energy. Let me make my J a little bit more clear so it's not connected like that. Well, E sub Rj is equal to, well, this one is nu prime R plus 1/2 plus, now we have B tilde, not prime, tilde, sorry, J times J plus 1. Here, R takes on the values 0, 1, 2, and so on. J takes on the values 0, 1, 2, so on. So notice there are two quantum numbers here in the total expression for the energy. And once again, this nu tilde is equal to 1 over 2 pi c times the force constant divided by the reduced mass raised to the 1/2 power. This is the fundamental frequency of the vibration. Okay, the fundamental frequency of the vibration. And B tilde is equal to Planck's constant divided by 8I pi squared c. All of the parameters are taken care of. This is the equation, the harmonic oscillator rigid rotator approximation, the mathematical equation that approximates what we see when we look at vibration rotation spectra is this. So the energy level diagram looks like this. I'm going to draw this one out by hand, actually. So what we have is, right, harmonic oscillator, R equals 0, R equals 1, R equals 2. Remember, the spacing between the energy levels is the same for the harmonic oscillator. R equals 3, so this is R equals 0, R equals 1, R equals 2, R equals 3. Within each vibrational level, there is a series of rotational levels. So we have J equals 0, J equals 1, J equals 2, J equals 3, so on. And then here we have this one, this one, this one, this one, this one, this one, and then for the R equals 2. For each vibrational level, there is a series of rotational levels. The spacing of the rotational levels is not the same, the energies. So, between each vibrational level, or for each vibrational level, which is the vibrational quantum number R, there are there is a progression of rotational states. There's a progression of rotational states. Okay. Now, when a photon of infrared is absorbed, not only does a vibrational transition take place from R to R plus 1, but several rotational transitions take place. Several rotational transitions take place. From J to either J plus 1 or to J minus 1. So right now we're talking just about absorption. So when we're talking about absorption, we're going to go from R to R plus 1. If we were talking about emission, we would be talking about going from some level R to R minus 1. But for the sake of absorption, we're going up one vibrational level, but the J level can actually go down or up. It could go from like J1 to J2 or J1 to J0. That's what this means. Okay, but several rotational transitions take place. When a photon of ion is absorbed, not only does a transition take place from R to R plus 1, but several rotational transitions take place from J to J plus 1. Yes, okay. Now, the selection rules. The selection rules, this is called vibration rotation. So when we look at a spectrum, it's called a vibration rotation spectrum. We can get pure rotational spectra. We can get information on pure vibrational spectra, but when we run a vibrational spectrum, what we get is a vibration rotation spectrum. We get a combination of the R jump and the J jumps. That's what's happening. So the selection rules. For vibration rotation are, well, we've already said it. Delta R equals plus or minus 1. Delta J equals plus or minus 1. If R is plus 1, that means it's going from a lower to a higher state. That's absorption. If R is minus 1, that means it's coming from a higher to a lower state. That's emission. That's all that means. In the case of delta J equals plus or minus 1, well, because you're actually going from one vibrational state, in the case of absorption, because you're going from, let's pick this one vibrational state to another vibrational state, the rotational state might go up 1 or down 1, but it still is sort of an absorption because it's actually going up an entire vibrational level. So you're still looking at a higher level. Okay. Let's look at the mathematics behind absorption. Okay. So what we want to do now is to derive an equation for the frequencies for the spectra that we see. Let's look at absorption. Okay, in the case of absorption, delta R equals plus or minus 1. Delta R is plus 1. It's absorption. Sorry about that. Delta J is plus or minus 1. Now, for R equals plus 1 and J equals plus 1, so we're going to have two cases, one plus 1, one minus 1. Plus 1, the frequency of absorption, well, the frequency of absorption is the difference between two energy levels. The frequency of absorption is nu what we observe or hope to observe? Well, it is the energy of the r plus 1 j, yes, r plus 1 j plus 1 state minus the lower state, which is the energy of the r and j. Okay, so now let's go ahead and do the mathematics here. This is going to equal this energy term minus this. So what we're going to have is prime times r plus 1 plus 1/2 plus b tilde times j plus 1 times j plus 2. This is the upper state minus the lower state, which is nu tilde times r plus 1/2 plus b tilde times j plus 1. I don't know if I should actually go through all of the algebra here. You know what? I think I actually will. At least I'll do it for this one. That's not a problem. So this is equal to nu times r plus 3/2 plus b tilde times j squared plus 3j plus 2 minus nu times r plus 1/2 minus b tilde times j squared plus j. I distributed the minus sign over both. What you end up with is nu tilde r plus 3/2 nu tilde plus b tilde j squared plus 3b tilde j plus 2b tilde minus nu r minus 1/2 nu minus b tilde j. This is just algebra. That's all it is. It's always the worst part of mathematics. Algebra has always been the worst. It always will be the worst. Don't let it get to you. I combine terms, like for example, I can cancel this one and this one. I can cancel bj squared and that one. I can combine the 3/2 nu minus the 1/2 nu. What I'm left with is nu tilde plus 2b tilde j plus 2b tilde. Let me simplify this a little bit. So nu observed is going to equal nu plus 2b. I'm going to factor out the 2b tilde, and this is going to be j plus 1, where j is going to take on the values 0, 1, 2, 3. This is very, very important. J here is the value of the lower rotational state. J is the value of the lower rotational state. In other words, the lower quantum number. The quantum number on the lower state. The value of the lower, it's the value of the rotation. Let me see. Is the value of the quantum number in the lower state. That's it. So this is one of the equations. This equation, for the different values that j takes on, what I'm going to see in the spectrum, what I expect to see in the spectrum is this. I expect to see a frequency at this number, this fundamental vibrational frequency plus 2 times this rotational constant times whatever the j value happens to be in the lower state. I expect to see a line there. Now, for the other case, for r equals plus 1, but this time j equals minus 1, the observed frequency that I expect is going to be the energy of the r plus 1 state, j minus 1, that's the upper state, is j minus 1, minus e r j. I go through the same algebra, and what I end up with is nu observed is going to equal nu minus 2bj. Here, j takes on the values 1, 2, 3, and again, j here is the value of the quantum number in the lower rotational state. Okay, that's why there's a difference between these two. All right, now let's actually see what this looks like. So this is the other equation that I'm interested in right here. Right? This gives me one set of lines for different values of j. This gives me another set of lines for different values of j. Okay. Let's see. So let's go ahead and go to a picture of the energy transitions to see what's happening first, and then we'll take a look at a spectrum. Okay, so these right here, the blue lines, this blue level, the lower, that's the lower vibrational state. That's, let me actually erase this. They use, most books tend to use this symbol V, or sort of a variation on nu, as the vibrational quantum number. I don't like that because it looks a lot like the frequency, and it tends to get really, really confusing, which is why I use R for the vibrational quantum number. So this is R equals 0, the 0 vibrational quantum state, and here this is the R equals 1 vibrational quantum state. Notice within each vibrational level there are several rotational levels: j equals 0, j equals 1, j equals 2, j equals 3, 4, and 5. And of course in the upper level it has its own rotational quantum states: 0, 1, 2, 3, 4, 5. Okay, what we see in the spectrum is a series of lines. For right now, let's not worry about what this Q branch is. Well, that's fine, I'll tell you in a second. So what's happening is R, the vibrational state, is going up by 1. So we're jumping up from this vibrational state to this vibrational state. Okay, so let's look at the R branch first. The R branch. The R branch of the spectrum. Here, the delta R equals +1 and the delta J equals +1. So notice, I'm going from, let me actually go to, you know what, that's fine, I'll just keep it blue. I'm going from the J equals 0, this line right here, this black line, is J equals 0 to the J equals 1. So I'm going, the vibrational quantum state is going up by 1. The rotational quantum state is going up by 1. The molecules that are in the state of J equals 1, they transition to the J equals 2. Remember, delta J equals +1. The 2 go up to 3, the 3 go up to 4, the 4 go up to 5. That's the R branch. The L branch, it represents, again, delta R equals +1. We're going up a vibrational state, but for the delta J equals -1. In other words, on the spectrum, I see a line for this transition, a line for this transition, a line for this transition, and a line for this transition. Now, for the L branch, sorry, left. The P branch, sorry about that. It represents a vibrational state of going from a lower vibration to a higher vibration, R equals +1, but the rotational state drops by 1. So here we're going from 1 to 0. J equals 2 to J equals 1. J equals 3 to J equals 2. J equals 4 to J equals 3. J equals 5 to J equals 4. There's a line for each of these transitions. So what we see is 1, 2, 3, 4, 5, and so on lines. And to the left we see 1, 2, 3, 4, 5, and so on lines. Now this Q branch, notice where the lines go. We're jumping up from a vibrational state to a vibrational state, R equals 0 to R equals 1. That's fine, that's not a problem. The selection rule can handle that. But we said that delta J has to be ± 1. Delta J cannot be 0. That's a forbidden transition. Notice this line right here. That's going from J equals 0 to J equals 0. J equals 1 to J equals 1. Because delta J equals 0 is a forbidden transition, these transitions, we don't see them in the spectrum. What you see in the spectrum is this empty, is no line at nu, the fundamental vibration frequency. Remember what we had just a second ago. We had a couple of equations. We said that for the R branch, we're going to end up seeing a bunch of lines at nu plus 2b times j plus 1. And for the P branch, we're going to see a bunch at nu minus 2b j. So there are going to be lines to the left, lines to the right of this number. But we don't actually see a line there because the transition of the delta j's, the delta j equals 0 transition is forbidden. So there is no actual Q branch. Now, there are molecules where the Q branch does show up. Your teacher may or may not decide to talk about it. We ourselves I'm not going to talk about it. It's not altogether that important, at least for what we're doing. But know that, so there is a P branch, there is a Q branch, there is an R branch. But in general, for the vibration rotation spectrum of a diatomic molecule, because delta J equals 0 is a forbidden transition, delta J has to equal plus or minus 1, we don't see a Q branch. It's just there's nothing there. Okay, now let's go ahead and take a look at the vibration rotation spectra. Okay, so this is a vibration rotation spectrum for HCl. Don't worry about this. This shouldn't even be in here. So this is vibration rotation of HCl. Now, you're going to sometimes see them this way in terms of they're going to be, the peaks are going to be pointing down. Other times you're going to see them where the peaks are pointing up. The R branch here, right here, see this? See these lines? This right here, see this little gap? This is the nu sub 0. This is the fundamental frequency. It's at this point where the J equals 0 to J equals 0 transitions should happen, but because they're forbidden, it's not going to happen. But that's where we see it. So if we want to know what nu 0 is, reading it off a spectrum, we just find that middle point and we go down and we mark it and we mark it. That's our nu sub 0. That's our fundamental vibration frequency. Now, the R branch, we said, is where you do it. Well, I'll just write it down. It's equals to that plus 2b times j plus 1 times j plus 1. Notice it's where the frequency, the absorption frequency, is going to be increasing from the fundamental frequency. The fundamental frequency plus a certain amount, fundamental frequency plus a certain amount, fundamental frequency plus a certain amount, plus a certain amount, that's the second transition, plus a certain amount, that's the third transition, plus a certain amount, that's the fourth transition, plus a certain amount, that's the fifth transition. So as the frequencies go up, that's the R branch. So this right here is the R branch. Over here, the frequencies go down. Fundamental frequency, the P branch, is the fundamental frequency minus some value as J increases. Minus, minus, minus. Notice these are going down. So this is the P branch. And like I said, sometimes you'll see it the other way. So when you look at these spectra, you're not looking at left and right. You're looking at R and P. R is for the frequencies that increase. P is for the frequencies that decrease from the fundamental frequency. That's what's happening here. Okay, so let's look at these lines. So the fundamental frequency is here. This one represents the transition from J equals 0 to J equals 1. This one represents J equals 1 to J equals 2. This one represents J equals 2 to J equals 3, J equals 3 to J equals 4, and so on. Here represents J equals 1 to J equals 0, J equals 2 to J equals 1, J equals 3 to J equals 2. This is the delta J equals plus 1. Here is the delta J equals minus 1. Now let's look at a spectrum that actually looks the other way. This is the spectrum for carbon monoxide. Sorry, I didn't write it on here. So this is the spectrum for carbon monoxide. In this particular case, the peaks are pointing up. So notice the increase. Oh, wow, this is kind of interesting. So the increase is still to the left is actually increasing, to the right is actually decreasing. Here is the fundamental frequency. Increase, this is the R branch. Decreasing, that is the P branch. That's it. That's all that's going on here. And because the equation is R nu plus 2b times j plus 1 and nu minus 2b j. The difference in the spacings, this difference right here, the difference between the lines, it's 2b. So spacing, the difference between them, 2b. That's it. We see absorptions. We see absorptions. So that's what's going on there. Now let's go ahead and see what else we have to say about this. Let's see. And once again, notice there is a non-existent Q branch here. Let's see. The frequency, the intensities. Oh, yes. Let's talk about the intensities. Notice that all of these lines, they have different intensities. Some are very, very intense. Some not so intense. Okay. Oh, this is the last page. The intensities, let me go ahead and, actually I'll write it over here, and I'll try to continue down here. The intensities of the transitions are related to the populations of each J level. The populations. In other words, if I have a bunch of molecules, let's just say I have 100 molecules in level 2. Well, 100 molecules in level 2, they're the ones, the more molecules that you have, the more transitions are going to take place. Well, that's why, let me see if I can get this right. The more molecules you have, each one of those molecules is going to make a transition. Each one of those transitions is represented by, is going to contribute to the size of the peak. Well, if you only have 10 molecules making the transition, let's say from level 3 to level 4, well, it's going to have a certain height of a peak. If you have 100 molecules making the transition from level 2 to level 3, that peak is going to be higher. So in this particular case, we see, notice that the level 2 to level 3 to level 4, those tend to be the peaks of highest intensity. That tells us that the rotational levels 2, 3, 4, those are the ones that are most highly populated at normal temperatures. So as far as the rotational state of a molecule, most molecules are not in their 0, 1, 2 rotational states at room temperature. Most of them tend to be in the 3, 4, 5 rotational states. That's where most of the molecules are. Therefore, the transitions that are going to take place, they're going to have the ones of higher intensity. Okay, so let me say that again. The intensities of the transitions are related to the populations of each J level. Of each J level. The greater the population of the level, well then, the greater the number of transitions. The greater the number of transitions. Therefore, the more intense the line. The more intense the line. Now, we see from these spectra that the J equals 3, 4, 5 are the most populated. That's all this says. Are the most populated. Okay, let's see. And once again, notice that the Q branch does not exist. That's because delta J equals 0 is a forbidden transition. Okay, thank you so much for joining us here at Educator.com. We'll see you next time for a continuation of molecular spectroscopy. Bye-bye.